Perhaps you've noticed them occasionally, those rare ghostly visitors that grace our night skies with their luminous tails stretching across the darkness. Like cosmic messengers from the distant reaches of our solar system, comets have captivated human imagination since we first gazed upward at the stars. Tonight, as you settle in and prepare for rest, I'd like to take you on a gentle journey through time and space to explore these mysterious travelers. Comets, often described as dirty snowballs or icy dirt balls, are among the most ancient and untouched objects in our solar system. While planets have transformed dramatically over billions of years through geological processes, atmospheric evolution, and in Earth's case, the emergence of life, comets remain largely as they were when our solar system was young, still in its formative stages. Close your eyes for a moment and imagine the early solar system, about 4.6 billion years ago. The newly formed sun sits at the center, surrounded by a swirling disk of gas and dust, the solar nebula. In this primordial cloud, small particles begin to collide and stick together, gradually forming larger and larger bodies. Some will become planets, others asteroids, and still others, those forming in the colder outer regions, will become comets. These primordial chunks of ice, rock, and dust hold within them a record of the very materials that built our solar system. They are time capsules, preserving the original ingredients of our cosmic neighborhood in a frozen state, largely unchanged for billions of years. What makes comets particularly special is their journey. Unlike planets, which orbit the sun in relatively stable, nearly circular paths, comets travel on highly elliptical orbits that take them from the frigid outer reaches of our solar system to the scorching heat near the sun, and then back again into the cold darkness. Some comets take just a few years to complete this journey. Others may travel for thousands or even millions of years before returning to the inner solar system. As you relax deeper, imagine following one such comet on its journey. For most of its life, it drifts in the distant frozen realms far beyond Neptune, either in the Kuiper Belt, a donut-shaped region extending from Neptune's orbit outward, or in the even more distant Oort Cloud, a spherical shell of icy bodies surrounding our entire solar system, like a cosmic cocoon. Here, temperatures hover near absolute zero, and the sun appears as just a particularly bright star among many. For millions of years, our comet sleeps in this deep freeze, dormant and unchanging. But eventually, perhaps due to the gravitational influence of a passing star or the subtle tug of the giant planets, its orbit is disturbed. It begins a long fall inward, toward the distant sun. As it travels closer to the sun over decades or centuries, the increasing warmth begins to affect its icy surface. When it crosses what astronomers call the frost line, roughly around Jupiter's orbit, the sun's energy becomes strong enough to begin transforming the ice directly into gas, a process called sublimation. This is where the magic begins. The warming ice releases not just water vapor but other frozen gases, carbon dioxide, methane, ammonia, along with ancient dust particles that have been locked away since the birth of the solar system. These materials form a cloud around the comet's nucleus called the coma. Meanwhile, the sun's radiation and solar wind push these released gases and dust away from the comet, creating the luminous tail, or often two distinct tails, one composed of gas that is pushed directly away from the sun by the solar wind, and another made of dust particles that trail behind the comet's path. These tails can stretch for millions of miles, sometimes spanning across vast portions of our night sky, yet they're so tenuous that stars shine right through them. What we see from Earth, that glowing visitor with its streaming tail, is a moment of extraordinary transformation. The dormant, frozen traveler awakens and shares its ancient materials with the inner solar system, briefly becoming one of the most spectacular objects in our night sky before returning to the cold outer regions where it will once again fall dormant. There's something profoundly poetic about these celestial wanderers. They connect the innermost and outermost parts of our solar system. They link the present moment to the distant past when our planets were still forming. They remind us that our cosmic neighborhood is not static but dynamic, full of motion and change. Throughout human history, comets have inspired wonder, fear, scientific curiosity, and artistic expression. Ancient cultures saw them as omens. Modern scientists see them as precious relics that can teach us about our origins. Tonight, as you drift towards sleep, we'll explore these fascinating objects more deeply. We'll trace their journey from the early solar system to the present day, examine their structure and composition, follow them on their orbital paths, and discover what they've taught us about our place in the cosmos. We'll also look at some of the most famous comets in history and the human stories that have become intertwined with these celestial visitors. So relax, breathe deeply, and let your mind float outward beyond our atmosphere, beyond the moon, beyond even the planets, to the quiet, cold regions where comets sleep and wait for their moment to grace our skies once again. To truly understand comets, we must first journey back to the very beginning, not just of these icy wanderers, but of our entire solar system. Close your eyes and imagine a scene from about 4.6 billion years ago, in a quiet arm of the Milky Way galaxy. Here, a vast cloud of gas and dust, mostly hydrogen and helium, but enriched with heavier elements forged in previous generations of stars, begins to collapse under its own gravity. As it contracts, it flattens into a spinning disk, with a dense center that grows increasingly hot until nuclear fusion ignites, giving birth to our sun. The remaining material in this disk, now called a protoplanetary disk, continues to orbit the young star. In the inner regions, closest to the sun's warmth, only rocky and metallic materials can remain solid in the heat. These materials gradually collide and stick together, building up larger and larger bodies that will eventually become the terrestrial planets: Mercury, Venus, Earth, and Mars. But it's the outer regions of this disk that particularly interest us tonight. Beyond what astronomers call the frost line, a boundary where temperatures are cold enough for volatile compounds like water, carbon dioxide, methane, and ammonia to freeze into solid ice, different types of worlds begin to form. Here, in this colder realm, ice becomes an abundant building material alongside rock and metal. The availability of these frozen volatiles allows for the formation of more massive planetary cores, which then gather large envelopes of hydrogen and helium, creating the giant planets: Jupiter, Saturn, Uranus, and Neptune. Yet, not all the material in this outer region ends up incorporated into planets. Countless smaller bodies also form, some rocky, some icy, some a mixture of both. Many of these objects are swept up by the growing planets, or ejected from the solar system entirely by gravitational encounters with the giant planets, particularly Jupiter and Saturn. But a vast population of these small icy bodies survives in the distant regions beyond Neptune. Some remain in a donut-shaped region we now call the Kuiper Belt, which extends from about 30 to 50 astronomical units from the Sun. 1 astronomical unit, or AU, being the distance from Earth to the Sun. Others are scattered even further out, eventually forming the vast spherical Oort Cloud that surrounds our solar system out to distances of perhaps 100,000 AU, halfway to the nearest star. These distant frozen reservoirs, the Kuiper Belt and the Oort Cloud, are the primary homes of comets. The Kuiper Belt is the source of what we call short-period comets, those that take less than 200 years to orbit the Sun. The much more distant Oort Cloud gives us long-period comets with orbital periods of thousands or even millions of years. Now, let's zoom in closer to one of these primordial ice balls as it sits in the distant Kuiper belt. What we're looking at is a time capsule, a preserved sample of the original material from which our planets formed. This comet nucleus is small by planetary standards, typically ranging from less than a mile to about 25 miles across. Its surface is darker than charcoal, reflecting only about 4% of the sunlight that falls on it. This darkness comes from organic compounds that have formed as cosmic radiation interacts with the ices over billions of years. Beneath this dark crust lies a mixture of ices and dust that has remained largely unchanged since it formed. About 80% of this ice is frozen water, but there's also frozen carbon dioxide, dry ice, carbon monoxide, methane, ammonia, and more complex organic molecules, the building blocks of life itself. Mixed throughout these ices are dust grains, tiny particles of rock and metal that were floating in the solar nebula before being incorporated into the comet. Some of these dust grains are even older than our solar system, formed in the atmospheres of dying stars and then scattered into space before becoming part of the cloud that would eventually form our sun and planets. As our comet sits in the distant Kuiper belt, it's incredibly cold, about -220 degrees Celsius, -364 degrees Fahrenheit. At this temperature, the ices are rock hard, and the comet is essentially dormant. It might remain this way for billions of years, silently orbiting in the outer darkness, preserving its ancient materials. But the solar system is not a static place. The giant planets, particularly Jupiter and Neptune, exert gravitational influences that can gradually alter the orbits of these distant objects. Occasionally, a passing star might also disturb the Oort Cloud, sending some of its comets inward. Through such influences, our dormant comet might eventually find its orbit changed, beginning a journey inward toward the sun. This journey may take hundreds, thousands, or even millions of years, depending on the comet's starting point and new orbital path. For most of this time, as it travels through the outer solar system, it remains dormant, a dark, frozen world reflecting little light and showing no activity. But as it crosses the frost line around Jupiter's orbit, the increasing warmth from the sun begins to affect the frozen volatiles. First to respond is the frozen carbon monoxide, which can sublimate, transform directly from solid to gas at very low temperatures. Then, carbon dioxide, then, water ice. As these materials transform from solid to gas, they create pressure beneath the comet's surface. Eventually, this pressure finds weak spots in the surface crust, and jets of gas and dust erupt, creating what astronomers call active regions. These jets feed the growing coma, a cloud of gas and dust that surrounds the solid nucleus. The coma can grow surprisingly large. While the solid nucleus might be only a few miles across, the coma can expand to be larger than Jupiter, or even as large as the Sun itself. Yet despite this enormous size, the coma is incredibly tenuous, a diffuse cloud of material that would appear as a vacuum by Earth standards. As the comet continues to approach the Sun, the solar radiation and solar wind, a stream of charged particles flowing outward from the Sun, begin to push the gas and dust in the coma away, forming the comet's tail, or rather tails, as comets typically develop two distinct types. The ion tail, sometimes called the gas or plasma tail, forms as solar ultraviolet light ionizes gas molecules in the coma. Once ionized, these molecules are strongly affected by the solar wind and are pushed directly away from the Sun in a straight, often bluish tail. The dust tail, by contrast, consists of tiny solid particles released from the nucleus. These particles are less affected by the solar wind and more influenced by the pressure of sunlight itself. They tend to lag behind the comet in its orbit, creating a broad, curved yellowish tail. These tails always point away from the Sun, not behind the comet in its orbital path as one might intuitively expect. This means that as the comet rounds the sun and begins its outward journey, its tails actually precede it, leading the way, rather than trailing behind. As our comet makes its closest approach to the sun, what astronomers call perihelion, its activity reaches a peak. The rate of sublimation increases dramatically, the coma expands, and the tails can stretch for tens of millions of miles across space. This is the comet at its most magnificent, a spectacle that if it passes close enough to Earth, might be visible to the naked eye, as a fuzzy star with a streaming tail, or even as a dramatic object stretching across a significant portion of the night sky. But this splendor is temporary. As the comet rounds the sun and begins its outward journey, it gradually cools. The sublimation process slows and eventually stops as the comet crosses back beyond the frost line. The coma dissipates, the tails disappear, and the comet returns to its dormant state, a dark frozen world silently traveling through the outer solar system. Each time a comet makes this journey, it loses some of its volatile materials, perhaps 0.1% to 1% of its mass with each passage. Eventually, after many orbits, the comet might exhaust most of its ices, leaving behind a dark, rocky object that resembles an asteroid more than a traditional comet. Astronomers call these objects extinct or dormant comets. Alternatively, a comet might break apart due to thermal stress from extreme temperature changes, gravitational stress from passing too close to a planet or the sun, or from the pressure of its own outgassing. Some comets end their lives by colliding with a planet or the sun, while others might be ejected from the solar system entirely after a close gravitational encounter with one of the giant planets. The life cycle of a comet is thus one of long periods of dormancy punctuated by brief episodes of spectacular activity. A cosmic rhythm playing out over thousands or millions of years. As we observe this cycle, it's worth noting that comets represent a connection between the innermost and outermost parts of our solar system. They transport material from the distant cold regions where they form to the warm inner solar system, depositing some of it along their path as their tails shed dust and gas. Over the 4.6 billion year history of our solar system, comets have played several important roles. They've delivered water and organic compounds to the inner planets, including Earth, potentially contributing to the conditions that allowed life to emerge on our world. They've occasionally collided with planets, sometimes with dramatic consequences, as when the comet Shoemaker-Levy 9 struck Jupiter in 1994, leaving visible impact scars in the giant planet's atmosphere. Comets have also served as natural laboratories for scientists studying the early solar system. Because they preserve materials from that distant time, examining a comet gives us a window into the conditions that existed when our planets were forming. The European Space Agency's Rosetta mission, which orbited Comet 67P/Churyumov-Gerasimenko from 2014 to 2016, and placed a lander on its surface, revealed a world of surprising complexity. The comet's surface featured cliffs, pits, boulders, and smooth plains. The mission detected organic molecules, including some of the building blocks of proteins, confirming that comets contain sophisticated carbon chemistry. NASA. As night deepens and you sink further into relaxation, imagine once more our comet, now making its way back toward the outer solar system after its brief moment of glory near the sun. Its activity is subsiding, its coma shrinking, its tails shortening as it moves farther from the sun's heat. It carries with it a slightly altered surface, changed by the intense period of sublimation it has just experienced. New active regions may have formed, old ones may have expanded, and some surface material has been lost to space. Yet, in its deep interior, it remains largely as it has been for billions of years, a preserved sample of the early solar system, continuing its lonely journey through the cosmic night. And as our comet recedes into the darkness, becoming once again a dim, frozen world far from human sight, we're reminded of the vast scales of time and space in which these objects exist. The brief period when a comet graces our skies perhaps a few weeks or months, represents just a tiny fraction of its orbital period, which might span decades, centuries, or millennia. This perspective invites us to expand our own sense of time, to recognize that the universe operates on cycles far longer than human lifespans, or even human civilization. Comets have circled the sun since long before our species evolved and will continue to do so, long after our time has passed. There's a certain peace in this realization, a sense that we are part of something much larger and more enduring than ourselves. Like the ancient ice preserved in a comet's nucleus, something of our own existence continues in the ongoing story of our solar system and the universe beyond. As you drift deeper into relaxation, perhaps a question has formed in your mind: how do we know so much about objects that spend most of their time in the distant, dark reaches of our solar system? How have scientists pieced together the remarkable story of comets, from their birth in the early solar system to their journeys through the cosmic void? The answer lies in a fascinating blend of ancient observations, modern astronomy, space missions, and laboratory studies that together have gradually revealed the nature of these elusive visitors. Humans have been observing comets for thousands of years. Ancient Chinese astronomers recorded their appearances as early as 1000 BCE. The Babylonians noted the passage of Halley's comet in 164 BCE. Medieval European and Islamic astronomers carefully tracked comets across the night sky, noting their positions relative to the stars. For most of human history, comets were viewed not as natural astronomical phenomena, but as atmospheric events or supernatural omens. Their sudden appearance, dramatic form, and unpredictable nature made them seem like messages from the gods or harbingers of momentous events, often disasters such as plagues, floods, or the deaths of kings. This perception began to change in the 16th and 17th centuries, as the scientific revolution transformed our understanding of the cosmos. In 1577, Danish astronomer Tycho Brahe carefully measured the position of a bright comet and demonstrated that it was farther away than the moon, proving that comets were celestial rather than atmospheric phenomena. A century later, in 1680 to 1681, observers including Isaac Newton tracked another spectacular comet. Newton used the comet's motion to test his newly developed theory of universal gravitation, showing that its path could be described as a highly elongated ellipse around the sun. This was a crucial step in recognizing comets as permanent members of the solar system, bound by the same gravitational laws that govern the planets. The most significant breakthrough in historical comet studies came from Edmund Halley, a contemporary and friend of Newton. In 1705, Halley analyzed historical records of 24 comets and noticed that the comets of 1531, 1607, and 1682 had remarkably similar orbits. He proposed that these were not three different comets but the same one returning approximately every 76 years. Halley predicted the comet would return in 1758, though he knew he would not live to see it. He died in 1742. When the comet did indeed return as predicted, it was named in his honor, Halley's Comet, and his work established beyond doubt that at least some comets were periodic visitors rather than one-time apparitions. This was a revolutionary insight, transforming comets from mysterious visitors to predictable members of the solar system. It also raised new questions. Where did these objects come from? Where did they go during their long absences from the inner solar system? What were they made of? The answers to these questions would come gradually over the next 2 centuries as astronomical instruments improved and our understanding of the solar system deepened. In the early 20th century, astronomers began to systematically study cometary orbits. The Oort Cloud, being much more distant, has not been directly observed. However, the orbits of long-period comets provide strong evidence for its existence, as they come from all directions in space, suggesting a spherical distribution of source objects, and many have never visited the inner solar system before, suggesting they come from very far away. While orbital studies were revealing where comets come from, spectroscopic studies were beginning to answer questions about what they're made of. By passing cometary light through a prism or diffraction grating, Astronomers could identify the chemical elements and compounds present in the comet's coma and tail. As early as the 19th century, these studies revealed that comets contained carbon, hydrogen, oxygen, and nitrogen, the basic elements of organic chemistry. Later work identified specific molecules such as water, carbon dioxide, methane, and more complex organic compounds. This chemical analysis supported the developing theory that comets were primarily composed of ice, dust, and organic materials, dirty snowballs, as astronomer Fred Whipple described them in 1950, or perhaps icy dirt balls given their often surprisingly low ice content. But the real revolution in our understanding of comets came with the space age, as we gained the ability to not just observe these objects from afar, but to visit them up close with robotic spacecraft. The first such encounter came in 1985, when the International Cometary Explorer spacecraft flew through the tail of Comet Giacobini-Zinner. A much more substantial investigation followed in 1986, when an armada of spacecraft from multiple space agencies encountered the famous Halley's Comet during its return to the inner solar system. The European Space Agency's Giotto probe came within 600 kilometers of Halley's nucleus, revealing for the first time what a comet's solid body actually looks like. The images showed a dark, irregularly shaped object with active regions jetting material into space, a far cry from the bright, glowing object visible from Earth, which is primarily the coma and tail rather than the nucleus itself. Subsequent missions have provided even more detailed views. NASA's Deep Impact mission deliberately crashed a projectile into Comet Tempel 1 in 2005 to study the material below its surface. The Stardust mission collected samples from Comet Wild 2's coma and returned them to Earth. And most spectacularly, the European Space Agency's Rosetta mission orbited Comet 67P/Churyumov-Gerasimenko for 2 years, deploying a lander named Philae to its surface in 2014. Rosetta's detailed observations transformed our understanding of comets. It revealed a world of surprising complexity, with diverse terrains including smooth plains, steep cliffs, large boulders, and circular pits. It detected organic molecules, including some amino acids, the building blocks of proteins. It measured the ratio of hydrogen isotopes in the comet's water and found it different from Earth's oceans, challenging theories that comets were the primary source of Earth's water. Meanwhile, laboratory studies on Earth have complemented these space missions. Scientists have created artificial comets by mixing ice, minerals, and organic compounds under low-temperature, vacuum conditions similar to those in space. When warmed, these mixtures behave remarkably like real comets, developing crusts and producing jets of gas and dust. Other researchers have analyzed meteorites that originated from comets, as well as interplanetary dust particles captured in Earth's upper atmosphere, many of which come from cometary tails. These tiny samples provide direct access to cometary material without the need for expensive space missions. Computer simulations have also played a crucial role in understanding comets. By modeling the early solar system, scientists can trace how comets formed and how their orbits evolved over billions of years. Simulations show how the migration of the giant planets, particularly Jupiter and Neptune, would have scattered the primordial population of icy bodies, sending some inward to become the asteroid belt and others outward to form the Kuiper belt and Oort Cloud. Together, these diverse approaches, ancient observations, orbital studies, spectroscopy, space missions, laboratory experiments, meteorite analysis, and computer simulations, have given us a remarkably detailed picture of comets. We now understand not just their physical and chemical makeup but their origin, evolution, orbital dynamics, and relationship to other solar system bodies. But perhaps what's most remarkable about this scientific journey is that it has not diminished the wonder of comets. And yet, for all we've learned, mysteries remain. We still don't understand exactly how comets form, how the diversity of cometary compositions arose, or the full extent of their influence on Earth and the other planets. Each new comet that visits the inner solar system, and each new mission we send to study these objects, has the potential to surprise us with unexpected discoveries. This ongoing journey of exploration reminds us that science is not a finished book, but a continuing story, one that grows richer and more nuanced with each chapter. Just as comets return to the inner solar system again and again, each time revealing more of themselves, so too does our scientific understanding deepen with each new observation, each new analysis, each new perspective. As night deepens, and your mind continues to drift among the stars, let's explore some of the most famous comets in history, the individual travelers whose visits have captivated, frightened, inspired, and informed humans throughout the centuries. These cosmic celebrities, each with its own character and story, have left their mark not just in the night sky, but in human culture, science, and imagination. The most renowned of all comets is undoubtedly Halley's Comet, named for Edmund Halley, who predicted its return. With an orbital period of approximately 76 years, Halley's Comet has been a regular visitor to the inner solar system for thousands of years, recorded by civilizations around the world long before its periodic nature was understood. The earliest confirmed observation of Halley's Comet appears in Chinese records from 240 BCE, though it likely was observed even earlier. It has appeared in historical accounts across cultures and eras. It was recorded by Babylonian astronomers, depicted in the famous Bayeux tapestry, commemorating the Norman conquest of England in 1066, and observed by astronomers in medieval Europe, China, Japan, and the Islamic world during subsequent returns. When Halley's Comet returned in 1910, it created a global sensation. It passed particularly close to Earth, with its tail sweeping across our planet. This proximity led to both scientific excitement and public panic, as spectroscopic analysis had revealed cyanide in the comet's tail, leading to fears of mass poisoning. Some entrepreneurs took advantage of the situation by selling comet pills and gas masks, though the extremely tenuous nature of the tail meant there was never any real danger. The 1986 return of Halley's Comet was less visually spectacular from Earth, as the comet's position relative to our planet was less favorable. However, it was scientifically momentous, as it was the first comet to be studied by an armada of spacecraft, including the European Giotto mission that provided the first close-up images of a cometary nucleus. The next return of Halley's Comet will be in 2061, when many children born today will be in their middle age. This predictable rhythm, this cosmic clockwork that spans human generations, gives Halley's Comet a special place in our collective imagination. It connects us to both past and future, to those who saw it before us, and those who will see it after we're gone. But Halley's Comet is just one of many cometary visitors that have left their mark on human history and science. Another famous example is the Great Comet of 1811, which was visible to the naked eye for an incredible 260 days, and at its peak could be seen even in daylight. It appeared during Napoleon's invasion of Russia, and was widely interpreted as an omen of the dramatic events unfolding in Europe. The Great Comet of 1811 is also connected to a more peaceful human activity, winemaking. Its appearance coincided with an exceptional vintage in many European wine regions, leading to the term Comet wine for the outstanding 1811 vintage. The comet's influence on the growing season was entirely coincidental, of course, but the association has persisted in wine lore. More recently, Comet Hale-Bopp put on a spectacular show in 1997, remaining visible to the naked eye for 18 months, a record for modern comets. At its peak, it was brighter than any star in the night sky except Sirius, with a distinctive blue ion tail and a separate yellowish dust tail that were easily visible even from light-polluted urban areas. Hale-Bopp was a long-period comet, with an orbit of approximately 2,500 years, meaning the last time it visited the inner solar system was during the early Iron Age, around 500 BCE. Its bright appearance in 1997 was due to its large size. Its nucleus is estimated to be about 60 kilometers, 37 miles in diameter, much larger than most comets. Unfortunately, Hale-Bopp's appearance was also connected to a tragic event, the mass suicide of 39 members of the Heaven's Gate cult, who believed that a spacecraft was trailing the comet and would take them to a higher existence. This grim episode reminds us that even in our scientifically advanced age, comets can still evoke powerful, sometimes destructive, responses in the human psyche. Not all famous comets are known for their spectacular visual appearances. Comet Shoemaker-Levy 9 gained scientific fame for a different reason. In 1994, it collided with Jupiter, providing the first direct observation of an extraterrestrial collision of solar system bodies. What made this event particularly fascinating was that the comet had been torn apart by Jupiter's gravitational forces during a close approach in 1992, breaking into at least 21 separate fragments. These fragments then crashed into Jupiter in July 1994, creating a series of massive impact sites, visible as dark spots in the giant planet's atmosphere, some larger than Earth. The Shoemaker-Levy 9 impact was a watershed moment in public awareness of the potential for cosmic impacts in our solar system. It dramatically demonstrated that such collisions were not just theoretical possibilities or events of the distant past, but ongoing occurrences that could be witnessed in real time. This heightened awareness contributed to increased support for programs to detect and track potentially hazardous near-Earth objects. Sometimes, comets become famous not for their visual appearance, but for the scientific breakthroughs they enable. Comet 67P/Churyumov-Gerasimenko was not particularly notable from Earth, a typical short-period comet with a 6.5-year orbit, discovered in 1969, but it became the most intensively studied comet in history when it was selected as the target for the European Space Agency's ambitious Rosetta mission. From 2014 to 2016, Rosetta orbited this comet, mapping its surface in unprecedented detail and deploying the Philae lander to its surface, the first controlled landing on a cometary nucleus. The mission revealed a world of surprising complexity and beauty, with diverse terrains, active jets, and a wealth of organic compounds. One of the most poignant aspects of the Rosetta mission was its conclusion. After 2 years of observations, as the comet moved away from the Sun, and the spacecraft's solar panels could no longer generate sufficient power, mission controllers deliberately crash-landed Rosetta onto the comet's surface. Its final descent provided even closer images of the comet before the spacecraft fell silent forever, now resting on the very object it had studied so intimately, a human-made artifact that will continue to travel with the comet on its ongoing journeys around the Sun. Comets sometimes become famous for the wrong reasons, when they generate excitement that turns to disappointment. Comet Kohoutek in 1973 to 1974 was predicted to be the comet of the century, based on early observations, leading to enormous public anticipation. However, it failed to brighten as expected, and was barely visible to the naked eye when it should have been at its peak. This led to the term pulling a Kohoutek to describe something that is heavily promoted, but fails to live up to expectation. A similar fate befell Comet Ison in 2013. Initially, this sun-grazing comet, one that passes extremely close to the Sun, showed promise of becoming spectacularly bright. Some astronomers speculated it might even become visible in daylight. However, Ison passed so close to the Sun that the intense heat and gravitational forces tore it apart. While its disintegration was scientifically fascinating, observed in real time by solar spacecraft, It meant that the anticipated naked eye spectacle never materialized. These disappointing comets remind us of the inherent unpredictability of these objects. Despite all our scientific knowledge, we still cannot reliably forecast how bright a newly discovered comet will become as it approaches the Sun. Each comet has its own unique composition and structure, and small differences in these characteristics can lead to dramatically different behaviors as they warm up. Other comets become notable for their unusual characteristics or behaviors. Comet Encke, for instance, has the shortest known orbital period of any comet, just 3.3 years. This frequent visitor to the inner solar system has been observed more times than any other comet, more than 60 returns since its discovery in 1786. Its short orbit has caused it to lose most of its volatile materials, making it more of a transitional object between a comet and an asteroid. Comet Hale-Bopp, which made a close approach to Earth in 1996, is remembered for having one of the longest tails ever observed, stretching more than 100 degrees across the sky from the perspective of some observers. This corresponds to a physical length of more than 500 million kilometers, 310 million miles, or about 3 times the distance from Earth to the Sun. Sometimes, comets surprise us by breaking apart, either due to gravitational stresses or the pressure of their own outgassing. Comet Linear fragmented dramatically in 2000, allowing astronomers to study the previously hidden interior of a comet. Comet 73P/Schwarzmann-Wachmann 3 began breaking into multiple pieces in 1995 and continued to fragment during subsequent returns, with over 60 pieces identified by 2006. Comets can even disappear entirely. Comet Biela was a periodic comet observed in the 19th century that broke into 2 parts during its 1846 appearance. By the next predicted return, in 1852, the 2 fragments had separated further. Neither was ever seen again, after that, presumed to have disintegrated completely. Interestingly, their disappearance coincided with the appearance of a new meteor shower. The Andromedids, also called the Bielids, believed to be debris from the comet's disintegration. This connection between comets and meteor showers is one of the most fascinating aspects of cometary science. Many of the meteor showers we observe annually are created when Earth passes through streams of debris left behind by comets on their journeys around the Sun. Each time a comet visits the inner solar system, it leaves a trail of dust particles along its orbit. When Earth intersects this trail, we experience a meteor shower, as the particles burn up in our atmosphere. The famous Perseid meteor shower of August, for example, is created by debris from Comet Swift-Tuttle. The Leonids of November come from Comet Tempel-Tuttle. The Orionids and Eta Aquariids are both produced by none other than Halley's comet. In a very real sense, when you wish upon a shooting star during one of these meteor showers, you're witnessing tiny fragments of a comet that may have been deposited in space thousands of years ago. Beyond their scientific significance and visual splendor, comets have played profound roles in human culture, religion, and art throughout history. Their sudden appearance, dramatic form, and unpredictable nature made them natural subjects for interpretation and symbolism. Comets can even disappear entirely. Comet Biela was a periodic comet observed in the 19th century that broke into two parts during its 1846 appearance. By the next predicted return, in 1852, the two fragments had separated further. Neither was ever seen again, after that, presumed to have disintegrated completely. Interestingly, their disappearance coincided with the appearance of a new meteor shower. The Andromedids, also called the Bielids, believed to be debris from the comet's disintegration. This connection between comets and meteor showers is one of the most fascinating aspects of cometary science. Many of the meteor showers we observe annually are created when Earth passes through streams of debris left behind by comets on their journeys around the Sun. Each time a comet visits the inner solar system, it leaves a trail of dust particles along its orbit. When Earth intersects this trail, we experience a meteor shower, as the particles burn up in our atmosphere. The famous Perseid meteor shower of August, for example, is created by debris from Comet Swift-Tuttle. The Leonids of November come from Comet Tempel-Tuttle. The Orionids and Eta Aquariids are both produced by none other than Halley's comet. In a very real sense, when you wish upon a shooting star during one of these meteor showers, you're witnessing tiny fragments of a comet that may have been deposited in space thousands of years ago. Beyond their scientific significance and visual splendor, comets have played profound roles in human culture, religion, and art throughout history. Their sudden appearance, dramatic form, and unpredictable nature made them natural subjects for interpretation and symbolism. As scientific understanding of comets developed in the 17th and 18th centuries, their cultural perception began to shift. They were increasingly seen as natural phenomena rather than supernatural omens, yet they retained their power to inspire awe, fear, and artistic expression. Mark Twain, the famous American author, had a particularly interesting connection to Halley's comet. He was born during its appearance in 1835 and remarkably died during its next return in 1910. He had predicted this cosmic coincidence, saying in 1909, "I came in with Halley's comet in 1835. It is coming again next year, and I expect to go out with it." And indeed he did, passing away one day after the comet's perihelion. Comets have inspired countless works of art, from ancient cave paintings and medieval tapestries to modern films and novels. They appear in the works of Shakespeare, who in Julius Caesar has Calpurnia say, "When beggars die, there are no comets seen. The heavens themselves blaze forth the death of princes," reflecting the ancient belief that comets heralded the deaths of rulers. In visual art, perhaps the most famous cometary depiction is Giotto's Adoration of the Magi, 1305, in which Halley's comet appears as the Star of Bethlehem, a connection suggested by some historians, though the timing makes it unlikely that Halley's was actually the biblical star. Even in our scientific age, comets continue to inspire art and literature. Carl Sagan's novel Contact and the film based on it feature the fictional comet Swift as a crucial plot element. Don DeLillo's novel White Noise uses a toxic chemical cloud, nicknamed the airborne toxic event, as a comet-like omen of death, hovering over the narrative. Fred Hoyle's novel The Black Cloud imagines an intelligent comet-like entity entering the solar system. Comets have also played significant roles in pseudo-scientific and apocalyptic thinking. In 1910, the discovery that Halley's comet's tail contained cyanide led to panic, with people buying anti-comet pills and sealing their homes against the supposedly toxic tail, despite astronomers' assurances that the tail was so diffuse that no harmful effects were possible. More recently, Comet Hale-Bopp became tragically connected to the Heaven's Gate cult suicide in 1997, as members believed that an alien spacecraft was hiding behind the comet and would take their souls to a higher plane of existence. Even as our scientific understanding of comets has advanced dramatically, they retain their ability to evoke powerful emotional responses, a testament to their unique place in the human experience of the cosmos. As we look beyond individual famous comets to consider these objects more broadly, we find that they play several crucial roles in our understanding of the solar system, and potentially in the development of life on Earth. Perhaps most fundamentally, comets are time capsules from the early solar system. While planets have undergone billions of years of geological processing that has erased most evidence of their primordial state, comets have remained largely unchanged since their formation 4.6 billion years ago. By studying them, we gain insights into the conditions and materials present when our planet and its neighbors were taking shape. This preservation extends to the most primitive organic compounds, complex carbon-based molecules that form the building blocks of life as we know it. Comets contain a rich variety of these compounds, including amino acids, the building blocks of proteins, nucleobases, components of DNA and RNA, and sugars. These aren't life itself, but they are the chemical precursors that, under the right conditions, could potentially lead to living systems. This observation has led to a fascinating hypothesis that comets may have played a role in the origin of life on Earth. During the early history of our solar system, Earth was subjected to intense bombardment by comets and asteroids. These impacts would have delivered vast quantities of water and organic compounds to our young planet. Some scientists propose that this delivery of extraterrestrial organic material may have been crucial for the emergence of life, providing such impacts can have devastating local effects, including massive tsunamis if they strike oceans, and global effects such as impact winters caused by dust and aerosols injected into the atmosphere, blocking sunlight and cooling the planet. While major impacts are extremely rare on human timescales, the threat is real enough that space agencies now track potentially hazardous objects and develop plans for deflecting them if necessary. Comets may also have more subtle but widespread effects on Earth's environment through their contribution to cosmic dust. As comets shed material during their passages through the inner solar system, they add to the interplanetary dust that constantly falls on Earth, an estimated 40,000 tons per year. This dust can influence our planet's climate and serves as nucleation sites for cloud formation in the upper atmosphere, creating phenomena such as noctilucent clouds. Looking beyond Earth, comets likely played similar roles throughout the solar system, delivering water and organic compounds to Mars, the moons of the giant planets, and other bodies. The presence of these materials doesn't guarantee the emergence of life, but it provides some of the necessary ingredients across a wide range of environments. Comets also serve as natural probes of the solar wind and the interplanetary medium. As they travel through space, their ion tails interact with the solar wind, making these invisible streams of charged particles visible. By observing how comet tails bend, break, and reform in response to solar activity, scientists can study the structure and dynamics of the solar wind across vast distances. Even the formation of comets provides crucial insights into the processes that built our solar system. The fact that comets contain materials that could only have formed at high temperatures near the sun, mixed with ices that could only have condensed in the cold outer regions, tells us that there was substantial mixing of materials across the early solar system. This mixing may have occurred through turbulence in the protoplanetary disk, the migration of planets that stirred up the disk, or other dynamic processes. Looking to the future, comets may play practical roles in humanity's expansion into space. Their abundant ice could provide water for drinking, growing food, and producing rocket fuel for deep space missions. Their organic compounds could support space-based agriculture or manufacturing. Some visionaries have even proposed that hollow comet nuclei, once their volatiles are extracted, could serve as natural spacecraft, ready-made habitats for human exploration and settlement. While such ideas remain speculative, they remind us that comets are not just objects of scientific curiosity, but potential resources that could support human activities beyond Earth. The first steps toward utilizing cometary resources may come within our lifetimes, as space agencies and private companies develop technologies for extracting water from asteroids and eventually comets. For now, though, comets remain primarily objects of scientific study and wonder, visitors from the outer solar system that briefly grace our skies before returning to the cold darkness from which they came. Each one that passes near Earth provides another opportunity to study these ancient, enigmatic objects, and to piece together more of the story they tell about our cosmic origins. As you drift deeper into relaxation, perhaps nearing sleep, imagine once more our comet, now having completed its journey through the inner solar system, and heading back to the distant reaches from which it came. Its brief moment of glory is past, its coma shrinking, its tails shortening, and eventually disappearing altogether, as it moves beyond the frost line where the sun's heat is no longer sufficient to vaporize its ices. For decades, centuries, or millennia, depending on the length of its orbit, it will travel through the outer solar system, a small, dark, frozen world invisible to all but the most powerful telescopes. Perhaps it will encounter the gravitational influence of a giant planet, altering its orbit slightly. Perhaps it will collide with another small body in the vastness of space, or perhaps it will simply continue its silent journey, unchanged and unchanging, until once again it falls toward the sun to repeat its transformation from obscurity to celestial spectacle. And as it travels, it carries within it a record of its journey, the altered surface created by its period of activity, the depleted volatile materials, the new patterns of cracks and vents formed by the stresses of heating and cooling. Like all of us, it is shaped by its experiences, changed by its journey, yet still fundamentally the same object that began its voyage billions of years ago in the swirling disk of gas and dust that formed our solar system. In this way, comets mirror our own experience of life, periods of dramatic activity and transformation, interspersed with longer periods of relative quiet, each leaving its mark, each contributing to the ongoing story of existence. Perhaps this is why these cosmic wanderers have captivated human imagination for so long, not just for their visual splendor or scientific significance, but for the metaphorical resonance they hold with our own journeys through time and space. As we near the end of our journey through the world of comets, you may be wondering about the current state of cometary science and exploration. What are astronomers and space agencies doing today to expand our understanding of these ancient travelers? What missions are planned to visit comets in the coming years? And what new technologies are being developed to study them more effectively? The study of comets remains an active and evolving field, with new discoveries continuing to refine and sometimes challenge our understanding of these complex objects. One of the most significant developments in recent years has been the recognition that the traditional distinction between comets and asteroids is not as clear-cut as once thought. We now understand that there exists a continuum of objects with various combinations of rocky and icy compositions. Some bodies that appear asteroid-like may be dormant or extinct comets that have lost most of their volatile materials through repeated passages near the sun. Conversely, some objects in asteroid-like orbits occasionally show cometary activity, leading to the designation main belt comets for objects that orbit entirely within the asteroid belt yet display comet-like behavior. This blurring of categories reflects a deeper understanding of the dynamic nature of our solar system. Bodies do not remain unchanged over billions of years, but evolve through processes such as outgassing, impacts, and gravitational interactions. What we observe today is a snapshot of an ongoing story of transformation and migration. Another area of active research is the study of interstellar comets, objects that originate outside our solar system and pass through it on hyperbolic trajectories that will take them back into interstellar space. The first such object, 1I/Oumuamua, was discovered in 2017, followed by the more obviously cometary 2I/Borisov in 2019. These visitors from other star systems provide a unique opportunity to study material that formed around a different star, potentially under different conditions than those in our early solar system. So while Oumuamua showed no detectable cometary activity, and had an unusual elongated shape. Borisov appeared more like a conventional comet, suggesting that comet formation may follow similar patterns across different planetary systems. The discovery of these interstellar visitors has prompted renewed interest in developing technologies to study such objects during their brief passages through our solar system. Various concepts for rapid response spacecraft that could be launched quickly to intercept future interstellar objects are being explored, though none have yet been approved for development. Closer to home, our ability to detect and track comets within our own solar system continues to improve. Survey telescopes such as the Zwicky Transient Facility, ZTF, and the upcoming Vera C. Rubin Observatory scan large portions of the sky repeatedly, identifying moving or changing objects that might be comets. These surveys are discovering comets at earlier points in their journeys toward the inner solar system, giving astronomers more time to prepare observations and potentially even space missions. Amateur astronomers continue to play an important role in comet discovery and observation. Despite the sophistication of professional surveys, individual observers with modest equipment still discover several comets each year. The worldwide network of amateur astronomers also provides valuable continuous monitoring of known comets, tracking their activity and alerting the professional community to unexpected events such as outbursts or fragmentations. In terms of space missions, while no spacecraft are currently visiting comets, several missions in development or operation will enhance our understanding of these objects. NASA's Lucy mission, launched in 2021, will study Jupiter Trojan asteroids that may share similarities with cometary nuclei. The European Space Agency's Comet Interceptor, planned for launch in 2029, will wait in space for a suitable target, ideally a pristine long-period comet entering the inner solar system for the first time, and then intercept it for a brief but informative flyby. Various other mission concepts are under consideration, including sample return missions that would bring cometary material back to Earth for detailed laboratory analysis, and landers that would perform extended studies on a comet's surface. The success of the Rosetta mission has demonstrated the scientific value of such ambitious projects, while also highlighting the technical challenges they present. Beyond dedicated comet missions, other space-based observatories contribute to cometary science. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is particularly well-suited to studying the chemical composition of comets. Solar observatories such as the Parker Solar Probe and Solar Orbiter occasionally capture comets as they pass near the Sun, providing unique perspectives on how these objects interact with the intense solar environment. Earth-based observatories are also advancing our ability to study comets. New facilities such as the Atacama Large Millimeter Submillimeter Array LMA in Chile can detect molecular emission from comets with unprecedented sensitivity and resolution, revealing the complex chemistry occurring within their comas. Adaptive optics systems on large telescopes can now provide sharper images of cometary nuclei and inner comas, approaching the level of detail previously only achievable with spacecraft. Laboratory studies complement these. Meanwhile, computational models of cometary physics and chemistry are becoming increasingly sophisticated. Modern simulations can track the complex interplay of gas and dust in cometary comas, model the thermal evolution of cometary nuclei over many orbits, and predict how comets might respond to various perturbations. These models help astronomers plan observations and interpret the results, while also contributing to our theoretical understanding of cometary processes. The study of comets also intersects with broader questions about the origin and evolution of our solar system and the potential for life beyond Earth. The ongoing debate about the contribution of comets versus asteroids to Earth's water and organic inventory touches on fundamental questions about the conditions that led to life on our planet. Similarly, the discovery of complex organic molecules in comets raises intriguing possibilities about the role these objects might have played in the emergence of life. While comets themselves are decidedly inhospitable to life as we know it, with their lack of liquid water, extreme temperature variations and exposure to radiation, the materials they contain and deliver to planetary surfaces could be important ingredients in life's recipe. This connection to astrobiology, the study of life's potential beyond Earth, ensures that cometary science will remain relevant as we explore the solar system and beyond. Each new mission to a comet, each new observation from Earth, and each new laboratory experiment adds another piece to the puzzle of how our solar system formed, evolved, and potentially gave rise to life. As we look further into the future, cometary science may take on practical dimensions beyond pure research. As mentioned earlier, comets represent potential resources for space exploration and settlement, with their abundant ices and organic materials. While near-term resource utilization will likely focus on more accessible asteroids, the development of technologies for mining and processing space resources will eventually make cometary materials accessible as well. There's also the matter of planetary defense, protecting Earth from potential impacts. While asteroids pose a more immediate concern due to their more frequent Earth-crossing orbits, long-period comets present unique challenges for impact prediction and mitigation. Their highly elongated orbits mean they spend most of their time in the outer solar system, potentially approaching the inner solar system at high speeds with relatively little warning. Developing better methods to detect and, if necessary, deflect such objects is an area of ongoing research. Even as our scientific understanding of comets continues to advance, these objects retain their cultural and aesthetic significance. The appearance of a bright comet visible to the naked eye remains a rare and special event that can capture public imagination and inspire interest in astronomy. Comet NEOWISE in 2020 provided such a moment, becoming briefly visible even from light-polluted urban areas and prompting many people to look up at the night sky with new appreciation. In this way, comets continue to serve as cosmic ambassadors, building bridges between specialized scientific knowledge and broader human experience. When a bright comet graces our skies, professional astronomers and casual stargazers alike share in the experience of witnessing one of the solar system's most ancient and enigmatic travelers. As we reach the end of our exploration, it's worth reflecting on how our relationship with comets has evolved over human history. From objects of superstition and fear, to subjects of scientific inquiry, to potential resources for future space exploration, our understanding of comets parallels humanity's broader intellectual and technological development. Yet for all our scientific progress, comets retain an element of mystery and wonder. We can predict their orbits with remarkable precision, analyze their chemical composition from millions of miles away, and even land spacecraft on their surfaces, but we cannot fully predict how a newly discovered comet will behave as it approaches the Sun, what surprises it might hold in its ancient ice, or what insights it might provide about our cosmic origins. This combination of scientific understanding and persistent mystery makes comets particularly compelling objects of study. They are simultaneously accessible, visible in our night sky, within reach of our spacecraft, and profoundly alien, formed under conditions unlike anything on Earth, and preserving a record of times and places far removed from human experience. As you drift towards sleep, carry with you this image of comets as cosmic time travelers, silently journeying through the vastness of space, occasionally gracing our skies with their ephemeral beauty, and connecting us to the deep history and boundless scope of our solar system. In their patient orbits and brief moments of glory, they embody something of the rhythm of existence itself, periods of quiet persistence punctuated by moments of transformation and brilliance. And perhaps, the next time you see a shooting star, a tiny piece of cometary dust burning up in Earth's atmosphere, you'll remember that you're witnessing the final act in a journey that began billions of years ago, when our solar system was young, and the complex story of our cosmic home was just beginning to unfold. As our journey through the world of comets comes to a close, let's take a moment to reflect on what we've explored together. We've traveled from the formation of the solar system 4.6 billion years ago to the present day, from the distant Oort Cloud to the inner solar system, from ancient human observations to modern space missions. We've encountered famous comets that have shaped human history and science, and we've delved into the ongoing research that continues to deepen our understanding of these remarkable objects. Throughout this exploration, comets have emerged as more than just astronomical curiosities. They are time capsules from the early solar system, potential contributors to life on Earth, natural probes of the space environment, objects of cultural significance across human civilizations, and possible resources for humanity's future in space. Few objects in our cosmic neighborhood connect so many different aspects of science, history, and human experience. As you rest now, perhaps drifting towards sleep, let the peaceful rhythm of cometary cycles accompany your thoughts. Imagine once more our comet, now receding into the outer solar system after its brief moment of activity near the Sun. Its surface has changed slightly from the heat and stresses of its inner solar system passage, but its deep interior remains much as it has been for billions of years, a preserved sample of the materials from which our planets formed. For decades or centuries, this comet will travel through the cold outer regions of the solar system, a small dark world moving silently through the void. The activity that made it visible from Earth has ceased. Its coma has dissipated, its tail has vanished. It has returned to its dormant state, carrying within it the ancient ice and dust that will remain frozen until its next approach to the Sun's warmth. There's something deeply calming about this cosmic rhythm, the slow, patient orbits that take comets from the frigid outer darkness to the warm inner regions and back again. In our fast-paced world, where we measure time in seconds, minutes, hours, and days, comets remind us of longer cycles, years, decades, centuries, millennia. They invite us to expand our temporal perspective, to recognize that we are part of processes that unfold over timescales far beyond individual human lifespans. This expanded perspective doesn't diminish the significance of our daily lives. Rather, it places them in a larger context. Just as a comet's brief period of activity near the Sun is a small but important part of its overall journey, so too are our individual lives meaningful moments within the broader tapestry of existence. Comets also remind us of the interconnectedness of our solar system. These objects that formed in the outer reaches bring material from those distant regions into the inner solar system, potentially delivering water and organic compounds to the early Earth. The meteor showers we observe today are created when Earth passes through streams of dust left behind by comets in previous orbits, tangible connections to these distant travelers. This interconnectedness extends to human culture and history as well. Comets have been observed by countless generations across all inhabited continents, interpreted through various cultural lenses, recorded in ancient texts and artworks, and studied with increasingly sophisticated scientific tools. They form a thread that runs through human experience, connecting us not only to our ancestors who looked up at the same celestial visitors, but also to future generations who will observe their returns. As you continue to relax, let your mind drift to the future. Perhaps imagine the return of Halley's Comet in 2061, when many children born today will be in their middle age. Picture the excitement as this famous visitor once again graces our skies, observed not just from Earth, but perhaps from lunar bases or Mars colonies. Imagine the sophisticated instruments that will study it, the new discoveries that might be made, the new questions that might arise. Or look even further ahead, to a time when humans might visit comets directly, not just with robotic spacecraft but in person. Imagine future explorers landing on a cometary nucleus, drilling into its ancient ice, extracting water and other resources that might support human presence in the outer solar system. These frozen worlds that have traveled through the solar system for billions of years might become stepping stones for humanity's own journey into the cosmos. These future possibilities grow from the foundation of knowledge we've built through centuries of comet observations and decades of space exploration. Each generation builds upon the work of those who came before, gradually expanding our understanding of these enigmatic objects and our place in the solar system. And yet, for all our scientific advancement, comets retain their capacity to surprise us. Each new visitor brings the possibility of unexpected behaviors, unusual compositions, or rare events like breakups or outbursts. The 2017 discovery of Oumuamua and subsequent identification of Comet Borisov reminded us that our solar system is not isolated but connected to the broader galaxy, occasionally receiving visitors from other star systems. This combination of growing knowledge and persistent mystery makes comets particularly compelling objects of study. We know enough to appreciate their significance and complexity, yet not so much that they've lost their ability to fascinate and occasionally bewilder us. They are familiar enough to be comprehensible, but alien enough to expand our thinking about the diversity of objects in our cosmic neighborhood. As sleep perhaps begins to approach, let this balance of knowledge and wonder, of science and awe, guide your thoughts. The same universe that operates according to precise physical laws that allow us to predict a comet's orbit with remarkable accuracy, also produces objects of stunning beauty and complexity that can still surprise our most sophisticated scientific instruments. In this way, comets embody something essential about our relationship with the cosmos. We study, measure, analyze, and theorize, gradually building our understanding of how the universe works. Yet we also experience wonder, beauty, curiosity, and occasionally reverence when confronted with the vastness, complexity, and sheer strangeness of the cosmos. Both approaches, the scientific and the experiential, are valuable and complementary. The scientific perspective gives us precision, predictive power, and practical applications. The experiential perspective connects us emotionally and aesthetically to the universe, enriching our lives and inspiring further exploration. Comets invite both responses. We can appreciate the precision of orbital mechanics that guides their paths, the complex chemistry that creates their comas and tails, and the geological processes that shape their nuclei. We can also simply marvel at their beauty as they grace our night skies, feel the connection to generations past who observed the same objects, and wonder at the ancient ice they carry from the earliest days of our solar system. As our journey together concludes and you drift deeper towards sleep, carry with you this dual appreciation of comets as both objects of scientific study and sources of wonder. Let the peaceful rhythm of their orbits, the slow, patient journeys through the outer darkness punctuated by brief, brilliant passages through the inner solar system, remind you of the larger cycles that continue regardless of our daily concerns. Somewhere out there, countless comets are silently traveling through space, some inbound toward future encounters with the sun, others outbound to the distant reaches where they spend most of their lives. They've been making these journeys since long before humans existed to observe them, and they'll continue long after our time has passed. Yet for a brief moment in cosmic history, we've developed the awareness and tools to recognize, study, and appreciate these ancient travelers. There's something profoundly comforting in this realization that we are part of a universe rich with beauty, complexity, and ongoing processes that transcend individual lives. Like a comet returning to the outer solar system, carrying the subtle changes from its recent solar encounter, you too carry the impressions of this journey we've shared: new knowledge, new perspectives, new connections to the cosmic story of which we are all a part. Rest well, and perhaps dream of distant icy worlds silently orbiting in the darkness, patient guardians of our solar system's ancient history, occasional visitors to our skies, and silent poets of the vast cycles that shape our cosmic home. Good night.